let us take a look at loaded spring combinations, special cases. In one case, there are two springs of spring constant, different spring constant K1 and K2 attached to a mass M. When we displace the mass M, the this spring and this spring will have the same extension, but the restoring force will be different because here the spring constants are different. Let F1 be the restoring force in this spring and F2 be restoring force in this spring. We know that F1 is equal to minus K1 into Y and F2 will be equal to minus K2 into Y, as the displacements will be the same in both springs. Now, the effective restoring force will be equal to F1 plus F2 minus times K1Y plus minus times K2Y. Taking y common and minus common, that is minus times K1 plus K2 into y. That means the effective spring constant is K1 plus K2. We can show that F is equal to minus times Ky, where K is the effective spring constant of this combination. Now let us take a look what will be the time period. The time period will be equal to 2 pi root of inertia factor, that is M. What is the spring factor? That is K1 plus K2. If K1 is equal to K2 is equal to K, in that case T will be equal to 2 pi root of M divided by 2K. Let us take another case. A mass M is attached to a combination of two springs having spring constant K1 and K2. When this mass is displaced in the vertical direction, the restoring force developed will be the F, but the extensions will be different. Let us say that extension produced in K1 is equal to Y1. So the restoring force in spring number 1 will be equal to minus K1 times Y1, and the restoring force in spring second will be equal to minus K2 times Y2. Now, the total extension produced Y will be equal to Y1 plus Y2, that is Y will be equal to, taking Y1 from this, that will be equal to F by K1, neglecting the negative sign. The negative sign tells us the restoring force is always opposed to the displacement, and this Y2 will be equal to F divided by K2. Now taking F common, Y is equal to F into 1 by K1 plus 1 by K2, cross multiplying it, that is K1 plus K2 divided by K1, K2 into F. Now going for the total restoring force, the total restoring force F will be equal to, cross multiplying it, K1, K2 divided by K1 plus K2 into Y. Now, if K is the spring constant of the combination, we can say that F is equal to Ky, where K is K1, K2 divided by K1 plus K2. Going for the time period, T is equal to 2 pi root of inertia factor, that is mass M, and spring factor, that is capital K. So T is equal to 2 pi root of M by K1, K2 divided by K1 plus K2. Taking the case K1 is equal to K2 is equal to K, that is T is equal to 2 pi root of M by K square divided by 2K. 1K and 1K goes, so T is equal to 2 pi root of 2M by K. Taking a look at case number 3, we have a mass that is placed between two springs. Those springs are attached to the rigid supports. That means when mass M is displaced, this will compress and this will extend. So the displacements of the both springs will be same. Let the restoring force F1 produced in this spring be equal to then minus K1 Y, and in spring number 2 will be equal to minus K2 Y. The effective restoring force will be equal to F1 plus F2, that is minus times K1 plus K2 into Y. Let this spring constant K1 plus K2 be substituted by capital K Y. So the time period, the equation of time period comes out to be 2 pi root of inertia factor, that is m, and mass factor, that is k, that is equal to K1 plus K2. In special case, if K1 is equal to K2 is equal to K, in that case time period will be equal to 2 pi root of m divided by 2k. So in this case, the extensions in both are the same. In case number 1, the extension is in both are the same. In case number 2, the extensions in both springs will be different. Thank you.